Okay, so let us begin. We continue our study of state space search, and what we have just seen is that the size of the state space can be significantly large even for the small toys that we talk about. So, in Rubik's cube we saw that the branching factor is 18. If you want to search up to depth 20, then you have to search about 10 raised to 25 nodes essentially. Even its smaller cousin, which is the 8 puzzle and the 15 puzzle. If you look at the 15 puzzle, where the branching factor is capped by 4, you can only move it in one of 4 directions. It is about 10 raised to 13 states, and the 24 puzzle is about 10 raised to 24 states. So, even that small puzzles that you get can generate huge state spaces essentially, and we have seen that 10 raised to 24 states is not a number that you can sniff at essentially, it will take you huge amounts of time. So, what is happening essentially is that the algorithms that we have seen so far are blind essentially, that given some state space, given some start state, what is the what is this algorithm doing with the goal that you want to achieve? It is using it only to test whether a given state is a goal state or not. It is not using it to guide its search in any manner at all. Depth first search, as we said, goes off in some direction and then it backtracks and tries other directions irrespective of where the goal state is. Breadth first search always circles around the start state and it will gradually expand its search frontier to move away essentially. The goal state has no role to play here essentially. So, the next step that we would like to do is to somehow exploit what we know about the goal state to help guide the search. So, let us assume that this was a city map essentially, okay, and let us say this S stands for IIT and you have to go to some place essentially. So, let us say this is a goal state somewhere. So, if you are consistent with the geography of Chennai, then this G could be maybe Marina Beach or something like that, somewhere in the northeast. If you want to go from IIT to Marina Beach, and you of course have to follow the roads, every junction is a node and every road segment is an edge essentially. So, in some sense being at a junction is a state. So, you are at IIT, so you are at this state, you want to be somewhere near the Gandhi statue in Marina Beach, that is a different state, and you can move across the road to move to a different junction which is a different state and so on. Now, imagine what these two algorithms are doing, they just go off in a predetermined manner essentially, and eventually of course if somebody tells them you have reached Marina Beach, they will say okay, I am done essentially. What do you really want? What you really want is an algorithm which would somehow head in this direction somehow. What do you mean by this? What we mean by this is that given a state, given a start state and given a set of successors, instead of choosing in a predetermined fashion which successor to inspect or expand as the term we use next, let us try to exploit whatever knowledge we can of the domain to help guide the search essentially. So, that is called as heuristic search. So, the word heuristic comes from the word, I mean there are various roots that I have read about. So, heurisco or heuriskine and so on. All these are sort of Greek words of Greek origin, and you might remember a word which is also related to heurisco, which is called eureka. This story of Archimedes running naked through the streets saying Eureka, Eureka and so on. Okay. So, what does Eureka mean? It means that I have found it or I have discovered it essentially, and this whole idea of heuristics is based on this knowing something essentially. So, how can we get heuristic knowledge? So, let me first discuss how this heuristic knowledge would be used essentially. So, we will assume that we have another function called h of n, which will take a node or a state and give a value which is a measure of, in some sense, how easy is it to go from that state to the goal state essentially. So, supposing we had such a function, so the theoretical community would say we have an oracle, it tells you what is the complexity of going from this state, or it tells you which, see, if somebody could tell you that of these successors or in general given an open list which one to pick next, then it would help, it would be helpful essentially, right, because then they would just tell you if you go here, if you go here, if you go here, you will reach the goal state essentially. So, first let us get this out of the way, this mechanism of how we are going to exploit the heuristic function. So, if you look at this algorithm that we have the same framework we will follow, open is initially made of this pair start. So, it should really be a list of lists essentially, and then extract the first one, extract the node, all that is the same, and we at some point generate new the set that we have of new nodes that we want to add to open. What we will do now, at least conceptually, is that, so remember that so far we said that we can either add new at the head of the tail of open or the remaining part of open, or at the end of the tail of open. If it was at the head of open, it was like a stack, if it was the tail of open, it was like a queue, but now we are saying is that something like this, sort on H, append new So, if I say append new tail of open, that part is like depth first search essentially, that new is added at the this thing. So, assuming append, that is what append does, it sort of takes this list and concatenates it with this list, putting them at this towards the head, it is like that this thing. But now I am saying after you have appended the two lists, sort them on the h value. What is h value? H value is this value of this heuristic function of the node essentially, which means what, simply that the best h value will come to the head of the list. We are still talking about it as a list, and this same algorithm will pick it from the head of the list and then this thing. So, if we have such heuristic knowledge, we can exploit it by simply modifying our algorithm to keep open as a sorted list, so that when we remove the head element, we always get the best element. What do we mean by best? By best we mean best according to what the heuristic function believes or what the heuristic function thinks essentially, only as far as that essentially. But if we have a heuristic function, then we can, so this is called a heuristic function, I should write it, right. It returns a number which is a measure of how easy or hard it is to go solve the state from there essentially. So, this is the only change we would need to make in our algorithm, that we have to sort the open list every time we add new elements essentially. Now, obviously, the data structure person inside you must be rebelling against this idea of sorting this list again and again and again, because sorting is expensive. So you could do other things. You could do, for example, merge, then sort new with tail open. Yeah, that is the first thing one thinks of. Okay, this is not needed. That because the number of new elements is going to be small and the rest of the tail is anyway sorted. So, just sort the new elements again on H, of course, and then merge it with the tail open, of course, which is a little bit better in terms of computational power, but that obviously is not the last word on this. So, just like we said that to make efficient use of closed, you must maintain it as a hash table. What about this open now? How do we efficiently implement open? So, of course, that efficiency will only be from the computational point of view. As far as the task is concerned of choosing the next successor, it does not matter in what manner we manage to sort it, how much time we spend sorting it essentially. But if you are concerned about that, how should you manage open? At the risk of turning this into a data structures class, we will spend 1 minute here. Yeah. So, you must maintain open as a priority queue. Of course, there are many different mechanisms to implement priority queues. We will not go into that. We will just make this observation that you must somehow implement open efficiently. So, what is really happening? Just imagine this, that we have this tail of open. This tail of open is like a big, let us say, sorted list or something like that, and then we have this new, which is a smaller list essentially. So, this is already sorted and we have got this new elements, and we have to sort of insert them into the right place inside this sorted list, and the best way to do it is by a priority queue, and one way to implement the priority queue is to use heaps, but there are other ways of doing it. So, you must, if you are implementing heuristic search, it is very important that you pay attention to how you manage open, because that is going to affect your running time essentially. Things become a little bit more complicated when you remember that you also wanted to remove from the new list those things which are already on open essentially, which is not the, for which the priority queue is not really the best way of doing things. So, I will leave this as a small exercise for you to, as a data structures exercise, you might say. You want to do both these tasks. You want to check for membership in open, that is a new node already present in open, which is best done by a hash table. You also want to maintain open so that always the best nodes will be at the head of open, which is what a priority queue does. How can you do both? Can you do both, and if yes, how we can do? But that is not our primary concern here. Our primary concern is to look at how heuristic search happens, and this is basically what is happening essentially. Now, let us pay attention to the heuristic function itself. How do we get this heuristic function? So, one thing that one can do is which is part of operationalizing this whole process, is that a search node which was originally a pair, which had the current node, the parent node. Now, we want to convert it into a triple. So, it will become current, parent, and let us just call it H value for that node essentially. So, we want to also store that h value onto the node, which means what, that every time we generate a new node, we will need to compute the h value. Let us say this is n is some node, and you want every time you generate a node n, you want to compute the h value for that node. Now, of course, you must keep in mind that this h value is not just the property of that node, it is also dependent upon the goal node essentially. For different goal nodes, the same node may have a different h value, but we are sort of glossing over that here a little bit essentially. So, how do we generate these heuristic functions? So, there are two approaches to this. One is domain dependent or static. So, by static we mean that it only looks at this current node and maybe it looks at the goal node in some manner, obviously it will have to do that and gives us a value back essentially. So, let us take an example, a couple of examples. Let us say this is a city map, like we said, let us say this is IIT and that is Marina Beach and so on and so forth. How can we give heuristic values to these nodes essentially? So, the simplest thing is h of n. So, city in a city map problem, route finding problem. So, nowadays of course, you have all these algorithms which do route finding for you, you have to go from one place to another. You must think about how they do this. You can say h of n. So, let us assuming that a goal node is given to us. So, what can we expect in a city map? We can expect to get coordinates essentially. So, start state is some x start and y start in a 2-dimensional map, and goal state is some x goal and y goal. If the coordinates are given to you, and that is reasonable to expect that the coordinates may be available in such a situation. How can we exploit this? How can we sort of get this? So, we say for each node or each location in the map, we compute the distance to the goal node, and that is a estimate of heuristic that we will use. So, one is Euclidean distance, and that is a good estimate of. So, how are we going to use this Euclidean distance? We are going to say, okay, these are the different places that you can go to. So, remember that in a city map situation, you are moving from one junction to the next, that once you are on a road, you have to go to the next, junction, which are these nodes here. So, essentially you compute this distance for each of these n nodes, each of the successors, and in general for every node in open, but to start with this is the only open that you have, and then choose the one which has which seems to be closest to the goal essentially. Now, this is a heuristic. So, when we say heuristic, we also use the term rule of thumb. And if you go to the Psychology Today website, they will say that it is a mental shortcut. A heuristic is a mental shortcut which we use to solve problems quickly. So, the emphasis is on the word quickly. We are trying to fight this combinatorial explosion and trying to use some knowledge in this case from the domain to guide our search. So, when you are using a domain dependent heuristic function, we have now 3 domain functions. One is the move gen function that we already talked about, and one is the goal test function, and the third is now the heuristic function, which means that if you are going to now create a new domain, you must write the programs which will compute h of n, so that the search algorithm can exploit it. As far as the search algorithm goes, it only uses that h value to sort or maintain a sorted list or maintain a priority queue of the candidates essentially, but the domain must now tell us what the h value is. We will in a moment we will try to see whether this can be done in a domain independent fashion at all, because you see this whole idea that we are trying to pursue is to write these algorithms in a domain independent fashion. We want to write these search algorithms without saying that I want to solve the city route finding problem or a Rubik's cube or a robot movement problem or a factory scheduling problem. It does not care. You have to find some general purpose algorithms, and we would like to plug in domains and just use those algorithms essentially. Yesterday there was a talk about this Mars rover. Is anybody attend? So, this NASA, they had this Mars rovers, and they use a lot of these kind of planning algorithms for finding paths for this, and it is not just the path for the robot to follow, it is also what are the movements that, for example, a robot arm must do if you have to pick up something from the ground, let us say a piece of rock from the ground or something. Every move has to be planned carefully, and they have used a lot of these techniques. Okay. So, a heuristic function, of course, if the heuristic function is perfect, which means it is like an oracle, what the theoretical computer scientists would say, then it will just tell you which is the correct thing, and then of course you would find the solution in linear time essentially. You just go from along the paths essentially, but in practice of course it is not so easy to find heuristic functions. What are the other functions that one can talk about? So, another function that we use sometimes is simply this xs minus xg. So, what is this doing? Instead of measuring, so the Euclidean distance is telling you the distance, as we say, as the crow flies. This is telling you a difference between the x coordinates and a difference between the y coordinates. What is the name of this distance function? Manhattan function, Manhattan distance. Also called as city block distance essentially, because if you have a nicely laid out city like Manhattan, then it is like on a grid, then you can only go along the roads on the grid, and the distance that you cover would be basically this, that if you had a grid, on a grid you can only move along the x direction or on the y direction. And there are other distance measures that one can think of. For example, one could take the max of this or max of this or max of this and this, sorry, and choose that, or there are other something called Minkowski norm, which we will not get into here. But so essentially what are we trying to do? We are trying to devise a domain function which takes two inputs, one is a node, given node, and the other is a goal node, which we assume that during the tenure of the search is constant. So, we are not mentioning it here, but it is there somewhere in the background, and it returns a value to us which gives us some idea of how close one is to the goal node essentially. So, in this context we can say a heuristic function is an estimate of the distance to the goal essentially. So, we are using the term distance explicitly here in this case essentially. In general, it is an estimate of how hard it is to solve a problem from a given state, and by hard we mean typically the number of moves that you want to make and later on when we see, we will see when we add cost to each move. So, for example, in a road we might add the length of a road or the congestion on the road as a cost or something, that we will come to that later. So far our idea of optimal solution is simply to have a smallest number of moves essentially. Let us look at another example, which is this 8 or 15 puzzle. So, let us say this is my given state, and I have, or let me choose one with 3 successes. So, I have 3 successes from here. One is that I can move this 2 down. So, I will get 4, 8, 2, 6, 7, 3, 1, 5, or I can move 6 this side. So, 2, 4, 8, 6, 7, 3, 1, 5, or I can move 3 up. So, let us say I have these 3 successors which I can make from here, and I have to decide which one of them to choose. So, obviously I need a goal state. So, let us say that we have some goal state which looks like this. So, let us say any state can be a goal state. So, let us say this is a goal state, and we want to somehow arrange the tiles so that we reach that state essentially. How can we talk about heuristic functions here? Can you think of a heuristic function? Now, what is a heuristic function, a static heuristic function? So, let us say we are talking about this state, this middle state where we have moved 6 to the left hand side. Is this a move that we should make? So, that is the question we are asking. Should we make this move or this move or this move? And so, we want to, for each of these we want to compute the h value as it is called, or the heuristic value, which basically should look at this only and that and tell us and give us a number. And let us say we will adopt the convention that the smaller the number the better for us, essentially with going with a sense of distance, the notion of distance. The smaller the distance the better. Can you think of a heuristic function? How?
How many tiles is it? The number of tiles in between, the distance from the tile.
Distance from its goal position.
Okay.
So, one function is, let us call it h1 of n is equal to sum of the distance for each tile, distance to goal. So, when I say distance to goal, I mean the distance to the goal position. So, just keep it in mind. And what do we mean by distance here? Let us assume that we mean the Manhattan distance, because this is a problem where actually distance has to be, it makes sense to use Manhattan distance because you can only move horizontally or vertically. So, what would be the heuristic value of this state? For this state we look at 2 is here and 2 is there. So, I will add 1 for 2, then 4 is here and 4 is there. So, I need 2 steps to get to that. So, 2 plus for 8 I need 1, 2, 3 steps. For 6 I need 1, 2, 2 steps. For 7 I need 1, 2, 3 steps. For 3 I need to move 1, 2, 3, 4 steps. For 1 I need to move 1, 2, 3 steps, and plus for 5 I need to move 0 steps. So, basically the sum of all these numbers. So, let me remove the, it is confusing here. So, I have all these numbers and basically the sum of all these numbers is the heuristic value for this state essentially. So, if you add it up, you will get a heuristic value. Likewise, you do for this and likewise you do for that, and you would have some way of making a guess which one is better. Can you think of any other heuristic function? It can be simpler than this.
Number of misplaced states.
Okay, that is another one. So, in this case H2 of n, you simply count how many tiles are out of place essentially. So, you can see in this situation 5 is in place and nothing else is in place, or if you want to count the blank tile as well, then you can say the blank tile is in its place, but that will anyway add up to something essentially. So, it is a simpler measure essentially, it is easier to compute, but is there a notion of better here? Is one heuristic function better than another? Supposing I were to tell you that these are the two heuristic functions to use, what does your intuition say? See, there are two aspects to making this choice. One is the cost of computing the function, and second is the benefit that it gives us. What is the benefit? The benefit that we are looking for is that we should guide our search better, or in other words, one way of counting this is that if you let us say run 10,000 experiments on this 8 puzzle, then you could compute something like this, a measure which we will call as effective branching factor equal to number of nodes seen divided by So, there is a parameter called effective branching factor. It is a property of the heuristic function, and the way it is computed is that you run an experiment. What does it mean? You give some start state, some goal state, and let the heuristic function guide search according to this algorithm that we have just written, and then count how many nodes did the algorithm see and divide it by the total length of the solution. What is the ideal value here? Ideal value is 1 essentially. If the heuristic function is perfect, you will only see the nodes which take you to this goal station. So, you will not see any other nodes on the thing. So, the ideal value for this effective branching factor is 1. The branching factor of the problem itself is known to you, which is 4 essentially. Okay, let us say it is bounded by 4. Or if it was Rubik's cube, it would have been constant 18, but in this case it is not constant, but let us say it is 4. So, the effective branching factor will be some value between 1 and 4. The better the heuristic function, and of course, you will not do it for one experiment, you will run thousands of experiments just to even out all statistical variations that you come by choosing different start states and that kind of a thing essentially. So, then you have a notion of one being better than the other. but at the same time you have the cost difference between the two. In this case these two functions, but in general there may be a choice of more than two functions. So, one has to choose a heuristic function essentially. Now, if you just go back to this algorithm again, it makes sense to use a heuristic function. If now remember that the heuristic function you have to compute for every node that you generate. Every time you call the moveGen function and generate the children, and after removing the duplicate ones, you have to compute the heuristic function for that node essentially. So, the extra cost of computing the heuristic function must be much less than the total time saved for this algorithm, which means that how do you save time? By seeing a fewer number of nodes essentially. If the heuristic function is good, then you will not go down some paths which are meaningless, and you will only go down the solution path essentially. So, obviously it makes sense to choose a, what should I use the term, inexpensive heuristic function, and the simplest or the most inexpensive ones are the static functions, which only look at a given state and tell you a value essentially. You show a state and it will say this is a good state or a bad state in terms of some number which it will compute using one of those things. Why do we say that? So let us go back to this city map example for a moment. What can happen which the heuristic function cannot foresee essentially. So, if you know the topology of Chennai, and if you know that, so you will go to the gate, you have no other option, you go to the main gate, and from there you have to decide where to go. And so, this is a starting place, that is a goal location. What happens when there is a river running across this? Okay, we have this Adyar river and it even has water sometimes. A heuristic function which is only looking at the start state and the goal state will be oblivious of the fact that there is a river on the way. Okay. So, in a mountainous situation it could be a pass, for example, you need a pass to cross a mountain range. Here you need a bridge. So, let us say the bridge is, one bridge is here and another bridge is here, but there is no bridge along the crow flies direction across the river. But what will a heuristic function do? It will drive the search in this direction, because it will tell you this node is better than this node and this node is better than this node. Whereas in actual practice these two, one of these two nodes is likely to be better. Why? Because this might take you to this bridge and this might take you to this bridge, whereas this will take you to dead end and then you will have to go down this path and then go like this. But not able to see in the future, a heuristic function will make judgment only based on what information it has. In this case it is a static function, which means the current location and the destination location, and based on that this appears to be the best. So, in that sense heuristic functions are fallible, that it is not necessary that they will give you the best. We will in the next class look at another example to see how a heuristic function can take you, can be misguided in some sense essentially, and we will discuss that in a little bit more detail. So, you have to devise some heuristic function which will give you a number for every node that you add to the open list, and we are assuming here that the smaller the better, because we are talking about the notion of a distance, and then we will sort the open list according to the heuristic function and always choose the best node, and the search will progress essentially. So, what is the hope? The hope is that the search will go towards the direction of the goal, but sometimes it may go in one direction and it may have to backtrack and try something else essentially. So, which one might say that you start with a search this thing, go down some path, okay, and you can fill in some values. So, that it will go down this path here. So, for example, this could be 40, this could be 60 and this could be 50 or something like that. So, it chose 40 and then likewise. Remember that all these are closed according to the algorithm and everything else is in open essentially. So, it is possible that the heuristic function will take you down this path and suddenly it will discover that the heuristic value has shot up at this stage. So, this becomes the next direction. So, the heuristic function is guided, since it is guided by the heuristic function, it does not always explore the space in the same predetermined fashion, but it depends on what is the goal that you have given to us. If the goal of was instead of here, the goal was here, let us say the Guindy station or something, then the search algorithm would have tried to go in this direction essentially. So, its behavior changes with every goal, that is a basic idea, that it is trying to go in the direction where the goal will be achieved essentially. Likewise for the other problems essentially. Okay, I will come to the dynamic functions in a moment. Let us discuss the properties of this algorithm according to the 4 criteria that we have talked about. Let us start with completeness. So, where should I write this? I think maybe here. Okay. So, let us give this algorithm a name, by the way, we have not given it a name, and this algorithm is called best first. Best first in the sense that of all the nodes in the open, it will pick the best one first, and what do we mean by best? The one with the lowest heuristic value. So, best first, what are the properties? Completeness, let us assume that it is a finite space for simplicity. It is complete. So, but how would you justify your argument? Actually, we did not actually give a very a little bit more formal argument even for the earlier searches, but we can give it now. Looking at this algorithm, how can you say that it is complete essentially? In every cycle, it picks one node from open, inspects it, and either puts into close or succeeds or whatever. The state space is finite, which means open can have only all the entire state space. In the worst case, it will explore the entire state space. In every cycle, it will inspect one node from open. So, it will terminate either when open is empty or when it is found the goal state. It will always find the goal state if it exists, because it will at some point enter the open, and it will always pick nodes from open, and open is a finite list, especially given the fact that we are removing the duplicates, we are never adding the same nodes again. So, the open has only the finite set to start with, and in the worst case it will pick them one by one and in every cycle and remove it and say I cannot find the solution. But when the solution exists, at some point it will be picked by open, picked by this step here, and it will say succeed. What is the difference between depth first and best first? The only difference is that best first is sorting, at least conceptually it is sorting the open list every time essentially. Though that is the only change, but it is going to pick every node once before it terminates. So, completeness follows. Let us talk about time and space in one breath here very quickly. What would you say? Time complexity, let us not worry about space so much at this moment. Yeah, let us talk about time. It really depends on how good the heuristic function is. Now you can see that if the heuristic function is perfect, then the time complexity will be linear. You will always go to the correct node. Linear in what? Linear in depth, right? So the depth is this search tree. You will always choose, make the correct choice at every level, and in linear time you will reach the goal state. In the worst case, it will be exponential essentially. If the heuristic function is bad, the heuristic function could be actually malicious essentially. Like, in some cities you find, ask somebody, how do I go there, and they will tell you the opposite direction. So even in the worst case, you will only do an exponential amount of search essentially. So it really depends upon the heuristic function. Likewise for space, it really depends upon the heuristic function. Now in the search tree that we were drawing like this was the open list for breadth first search, and the open list for depth first was like this. Now it is really difficult to give you a feel of this exponentially growing open list for breadth first search, but you must keep in mind that every time when I go from one level to the next, I am multiplying the length, if you want to call it, by b essentially, where b is a branching factor, which is not really depicted in the diagram. This is just kind of a schematic diagram, but every time it is becoming longer by b essentially. So therefore it is growing exponentially, whereas the for depth first search, the open is basically kind of proportional to length, and it is linear, that we have argued so far. It turns out that for best first search, typically the search frontier looks like this. Okay. Now this is typical, of course, which means it is not really linear, and it generally tends to be more towards exponential in nature in practice essentially. There is one thing that you should consider if you have solved this kind of problems, or if you have solved the Rubik's kind of problems. Just try to imagine that sometimes you have to go against the heuristic function. We will come to this point later, in the sense that if you are counting, for example, the number of tiles in place or something like that, then at some point you have to disrupt something that you have already done. So for example, in the Rubik's cube you have done the top face, and then to do the second layer you have to temporarily disrupt the top face. Now heuristic function would be very upset about such things. You have made the top face and then you are disrupting it. It will not reflect nicely in your search essentially. So we will come to those issues later. Completeness, time, space, and what else? Quality. I will defer this discussion to quality later. Just think about it. Do you think that this will give you an optimal solution or not? And we will come to this later. I just want to spend a couple of minutes on the other side, which is the domain independent. And without going into details, I will just say this, that a domain independent heuristic function solves what we call a relaxed problem. So it solves a relaxed problem, and so what is the key difference? The static function only looks at the given state and the goal state and gives you a value. The relaxed problem, and when we look at planning, we will see, if we get time we will look at this in a little bit more detail, but the relaxed problem is modifying the original problem so that it can be solved more easily essentially. So to give you an example, when you look at the 8 puzzle like this, now if I have to go from 2 to, if 2 has to go here, or if 2 has to, let us say if 7 has to go here in place of 1, So, you want to move 7 to 1. Now, in the real 8 puzzle you have to first move 8 out of the way, then you have to push 7 up, then you have to somehow create a gap by pushing. So, you have pushed 8 here, then you push 6 and then 5 and then 4 and then 3 then 2 and then 1 and then you push 7 up essentially. You have to do a lot of moves in the real world essentially. But imagine an 8 puzzle in which you can slide on top of other slides or sit on top of other slides, other tiles essentially, which means I have modified my problem that I can make a move where 7 can come here and then it can come here. It does not have to be a blank tile to move into, which is the real problem essentially. The relaxed problem you can move over on a tile and sit on top of another tile. Now, you can see that if I am working with this relaxed problem, I can easily find how many steps it takes for me to go from 7 to 1, which is 2 steps. Now, which when we devise the static function also we gave the same value. Remember the distance to the goal step is it. The difference between the static and this dynamic domain independent function is that the static domain function was devised specifically for the 8 puzzle, whereas when we learn how to sort of pose problems in a uniform manner, we can see that we can pose problems and then we can pose relaxed problems in a domain independent fashion and they can be solved typically in polynomial time. That is a key thing. Okay. So, what is the difference between a static function and a dynamic function or domain independent? A static function we assume is solved in constant time, because it only looks at a given state and the goal state and gives you a value, whereas this domain independent function actually explores the space, but under different constraints which are relaxed from the original problem. So, it still may search up to a certain depth essentially, but the problem has been relaxed to such an extent that to solve the relaxed problem it needs only polynomial time. That is a general idea. We will try and come back to that later, but it is done in a domain independent fashion. I just illustrated it with the 8 puzzle here essentially. So, what happens now? You have a heuristic function which is computed whenever n is generated. With a static function this is computed in constant time. So, obviously it is likely to be helpful. The question is, if I have a polynomial time function sitting here, is it going to help? It is attractive because then I can do this in a domain independent fashion. I do not have to say, oh, this is a city map, I can use the Euclidean distance, or that is a 8 puzzle, I can, or that is a Rubik's cube and I can count the red tiles and the blue tiles. I do not have to do any of that reasoning. I will say in some well defined manner I will change the problem definition to such in such a manner that it can be solved in polynomial time, and then the length of that solution I will use as a heuristic value here. So, you have plugged in a polynomial function here and the question is, does it help? You have plugged in this polynomial function inside this thing which is basically exponential in nature, and the answer is that yes, in practice it helps, and we will see that a little bit later. But to generalize, the idea of using a heuristic function is to use a function which will, given the choices you have, given the open list that you have, it will tell you which node to inspect next, rather than do it in a blind fashion like depth first or breadth first, or for that matter DFID was using. It is using some, it is doing search in a more informed fashion, and that is why it is called best first search. So, we will take up best first search again and then we will try to improve upon this a little bit. We will come back to this notion of quality and completeness and revisit them essentially. Keep in mind that time and space complexity on the average are still exponential in nature. They may be better exponential functions than the original, but they still tend to be exponential, except of course in some domains where the heuristic function is very nice, easy to build, in which case you will get a lot of improvement. For example, if you are in Manhattan, then you can find the path quite easily. Okay, so we will come back to this in the next class.